So let's get started with some forcing. So we envision we have an oscillator that oscillates at a certain frequency. So let's maybe just, in this example, just write some oscillator down. We're not going to really use that equation, but just so, for concreteness. So we have some oscillator. This would be a harmonic oscillator with frequency omega naught squared and some damping. And then let's just throw in some nonlinearity, and it's being forced. So f of t is our forcing. And the question is, how do we now incorporate that into our analysis, that there's this forcing term? Of course, so we expand in y, but what about the f part? So it turns out that it's actually useful to extend the system again, somewhat similar to when we did previously, when it went from the Zener manifold at the bifurcation point to the Zener manifold where we included the control parameter as a dynamical variable, which then turned into a nonlinearity. So we can do that similar here, that we assume that f is actually part of the dynamical system. So we can write down a differential equation for f, which would be like, for instance, like this. So we have simply f double prime plus omega squared f is equal to 0. And so this would oscillate with a frequency omega, whereas this guy, the oscillator that we're talking about, has a natural frequency omega naught. And in general, they don't have to be the same. They may be whatever. And in fact, that's sort of what we're going to focus on, particularly how the result of this coupling depends on the ratio or the relationship between these two frequencies. Okay, so let's maybe first assume, for starters, that these two frequencies are not related. So that means they're irrationally related. I mean, let's assume they're irrationally related. So omega naught, or let's say omega, is equal to alpha times omega naught, where alpha is irrational. So there's no, so omega over omega naught is not a rational number. So that will play an important role later. So let's now do the expansion as we would. So we have two equations. We expand those guys in their amplitudes. So let's say we have y is given by some amplitude, which will depend on slow time, times e to the I omega naught t, right? So what we would be doing if we really went through the details, we would first look at the linear part of this equation, do a linear stability calculation. We would find out that at least in the absence of damping, so let's forget about the damping for a moment, this oscillator would have a frequency of omega naught, and therefore the linear eigenmode would be e to the omega naught t. We can talk about the damping later. It turns out to actually include it in this kind of analysis. We really should assume beta is small, but let's not worry about that right now. So the main point is that we just expand y in this form. I've not put an epsilon there because we're not going to do it that explicitly. We're just looking at orders in A, so fine. And then of course we have the complex conjugate, e to the minus omega naught t, plus higher order terms. And analogously, the f of t will be some amplitude capital F, which I guess could also depend slowly on time, why not? E to the I omega t, plus f star of t, e to the minus omega t, and no nonlinear terms, so no higher order terms, full stop, because this is just a linear equation, right? We're just having a linear equation. Good. So, and now we're in business, because now we can do what we said before. I should have said that earlier, maybe. I mean, the way we deal with this is the tool we've developed is that we assume the system has, or we consider systems that have a continuous time translation symmetry, where we can shift the time arbitrarily. So if you were only looking at this equation alone, with not an additional equation for f, but just assumed f was time dependent, then this differential equation here actually does not have constant coefficients, right? So it's not time translation invariant because f is not constant in time. But now, since we've written this as an extended system, the extended system has no time-dependent coefficients because these coefficients here are all constant, right? So the time dependence of f comes now about as a dynamical equation. And so therefore we can use exactly the same approach as before, where we say, okay, the system is invariant under time translations. And so if we make an arbitrary shift, then what happens? Well, if we go from t to t plus delta t, then if we look at our A equation, well, then we get A goes to A times e to the I omega naught times delta t. Right? So if you shift this t by delta t, you can absorb this e to the I omega delta t into the A. So you have the action on A given by that. And similarly, the action on F is F goes to F times e to the I omega times delta t. So the important point is that this phase factor and this phase factor are different from each other. Okay, good. So then what did we do? Well, we said once we do this expansion, we envision the expansion without actually doing it, we will get equations for A and F. So we'll get an equation dA by dt is equal to some function F, let me call it FA. Oh, that collides with the other notation for F. So let's make that a curly F FA, depends on A and A star, on F and F star. And similarly, there's an equation for F, which is curly F, which depends on, well, okay, in principle, in the most general case, this would also depend on A. But in our case, we really just have this additional equation for F, which is not coupled back to A. And so this guy here only depends on F and F star. Okay, and moreover, this equation is actually linear, right? So this looks like making things way more complicated than it would have to be because this is just a simple linear equation. We know the solution, here it is, and so on. But it actually, for this formalism, this is a very elegant way to deal with the time-dependent coefficient. Okay, and so now we have to do our selection rule business. So what is the selection rule? So F, both functions F are polynomials in A and F and so on. And as I said, we don't have to consider the function F for F. We only need to consider FA, right? So that is going to be some polynomial. So the general term will be, let's write down, there will be a general term in that function curly FA will be something like A to the K power, A star to the L power, times F to the M power, times F star to the N power. So that's the general term here. And how does that transform under this action, right? So we need to look at this term when you apply this action. So allow me to write that like this. So this goes like to A, okay, let me first copy back what stays the same. And then what do we get? We get e to the I, and from the A, we get e to the I omega naught delta t times K minus L times e to the I omega delta t times M minus N. So that's the general term on the right-hand side. On the left-hand side, of course, there's just an A. So we know that this exponential phase factor, this phase factor, has to be the same as this phase factor. And on the left-hand side, we have, maybe I should write that down once more, dE by dt goes to e to the I omega naught delta t times e dA by dt. And so we have that both of these terms, this guy and this guy, have to, oh, this light is getting interesting. Okay, sorry about that. They both have to transform the same way. And so that means that we need that omega naught delta t is equal to omega naught delta t times k minus L plus omega delta t times m minus n. So now comes the important part where we need to state something about the relationship between omega and omega naught. And as I said, right now I want to consider the case where they're irrationally related. That means that there's no integer number m minus n that would make this real number equal to this minus this. So in other words, this term here, this term has to vanish by itself, as do these together, because alpha is irrational, right? Let me emphasize that again. And so we get the condition that k minus L equals 1 and m equals n. Okay, so the most general term therefore looks like we have a term which is a to the k, so it's a, k is L plus 1, so I can write this as L plus 1 times a star to the L power times f to the m, but m is the same power as n, so f to the n, f star to the n. So this term looks like this. It's an a absolute value squared times a times f, well, not absolute value squared, 2L power, f absolute value to the 2n power. So that's the most general term that is possible in this case where the forcing is not related in its frequency to the oscillator. So that's still a lot of terms, but as we said before, all of that is meant to be an expansion for small a and also for small forcing. So we really consider small forcing or small amplitude and weak forcing, let's say. Small amplitude and weak forcing. So we're really looking for the term that is dominant when the forcing is very small. And so lowest order term in the forcing, therefore, is the lowest order term here in the forcing is, well, n could be 1 and L could be 0. So the lowest order term is actually a times f absolute value squared. That's the lowest order term. So assuming we want to have now an equation which is also well behaved when we have no forcing. So I would think, we have a half bifurcation and we would like to have an equation that describes the half bifurcation as in, let's assume it's supercritical, so the amplitude saturates. And so we have a nonlinear term that's saturating. So that means I would like to have a cubic term only in A, which saturates without forcing. Because I imagine I have an oscillator that does this thing, and then I turn on the forcing. Okay, so if that's the case, then I will have a term a squared, a absolute value squared times a. And if we want to balance these two, because as I said before, the approach is that we'll get an equation, we want to have an equation which includes all the relevant terms in the same order. And so therefore we would have something of the order that a cubed has to have the same order as af squared. So f is of the same order as a. And so then we get the two leading order, the following equation. We get dA by dt is equal to, well, there's a term from just the half bifurcation, a linear term. And there's a term from a absolute value squared a. And now the new term here, where is it? our new term that can be put in here with some, I guess there could be a coefficient, let me call it mu2, f absolute value squared, like that. So that's the equation we get to leading order for weak forcing and small amplitude. So let's think about that equation. What do we have here? The first thing we notice is that even though we have now forcing, there's no new term in the equation. We have the good old cubic term and the good old linear term. So in that sense, the bifurcation, if we now did an analysis of this equation, that analysis will be exactly the same. The only thing that's different is that we have here a coefficient where it's not just the bifurcation parameter mu, but also the forcing. So the forcing modifies the bifurcation parameter, or the linear growth rate, and that's all it does. Okay, so that's a very simple situation. So not much happens. If you force non-resonantly, meaning with a frequency that's not related to the frequency of the oscillator, that's really irrationally related only, then the only thing that happens is that you shift the bifurcation point. Okay. Let's comment on something more. In general, of course, we have that f shows up for all powers of a, right? The general term has an f squared or f to the fourth, for all these powers. So why do we only have it show up here? Well, all the other terms would be higher order. And it's pretty clear why that is the case. I mean, if you look at the equation, the dA by dt term has an order 1 coefficient in front. I mean, actually, it is 1 right now, but the cubic term in general also has an order 1 coefficient in front. So that means if you now were to include, say, a term a absolute value squared a times f squared, the f squared or f absolute value squared is small. So that would only modify this coefficient gamma a little bit. It would be a small correction to this coefficient gamma. And so unless this gamma happens to be small, which it usually is not, that small change is really not very important, and we just leave it among the, it's a higher order term and we happily ignore it. The coefficient mu, however, that almost by definition is small because that's the control parameter which goes through 0, the growth rate goes through 0 at the bifurcation point. So since we are expanding around the bifurcation point, this is by definition small. And there, the small change due to the forcing can make a significant difference. In fact, we can change the sign of mu, right? Mu could be positive, but if mu2 is negative, sufficiently strong forcing would actually make this negative, for instance. And so that's why the equation, this is sort of the nutshell capturing all the relevant information that is to be had for irrational or non-resonant forcing.